how much energy comes out to use 55.3. We'll go to 55.3 grams of C2H4. Grams is mentioned, so we're going to need the grams per mole here. 2 times 12.01, this is carbon. H, there's 4 of them. That'll be 24.02, this will be 4.04. 28.06 grams per mole for this. I want grams on bottom, so I'm going to put 28.06 grams of C2H4 to 1 mole. And now 137. So before I was given moles, and I could just use that to calculate the energy. Here I'm given grams, so I need the grams per mole, and then this relationship to find it.
I think you would explain it, or you just explain one more time why you don't use negative for the 137 reactions or something.
We know that energy is released because of that. And the question says, it's sort of like, how do I put it? If the question is phrased, how much energy is released, it's sort of like saying, if you left here with $20 and you came back here with $15, and I said, okay, everybody, how much energy, or how much money is she down? You could say $5, and the negative is implied because I said, how much is she down? How much money is she down? But if you left here with 20 bucks and came back with 25, I would naturally say, how much money is she up? So it's the phrasing that gives you the idea that it's absolute value. I wouldn't say, if I said, what is her delta money when you came back with $15 instead of 20? Then you'd say, yeah, it's negative 5. But if you came back with $25 and I said, what is her delta money? Your delta money is plus 5 if you came back with $25. But the plus is handled if I say, how much money is she up now? So the plus is implied there. And if I said, you came back with $15 and I said, how much money is she down? The down is implied. So the answer to the up-down question is just the absolute value, because I've already said up or down. But I said, what is her delta money? The delta is negative if you're down 5, and the delta is positive if you're up 5.
So if I see the word that released, I know I don't want to put
Yeah. If it says released or absorbed, the sign was already handled. Okay, some of these ask you for, instead of asking you for energy, number 4, kilojoule per meter, that's very similar to that one. Okay, this one. This is number 5.
Yeah, sorry.
So number 5 here is the reaction is C3H8 plus 5O2 3CO2 4H2O. There's the reaction, and it tells you delta H is negative 531 kilojoules. So we know energy is released, aka we know that it's exothermic. This one's in calories, kilocalories. Calories is just a different unit for energy. Calories being joules. Energy. That much energy is released, then how many moles of, it says propane. This is propane. So how many moles of propane? It just says burn instead of reactive because this is a combustion reaction. It's supposed to say burn. So in this case, you're going to go 1.24 times 10 to the 5 kilocalories are burned. And then 531 kcals to 1 mole C3H8, which is propane. And that'll tell you how many moles. 1 divided by 1.24 divided by 531, whatever that comes out to be, times 10 to the 5, will give you the moles. You guys okay with that? If this asked how many moles of CO2, if it asked about CO2, then I would have a 3 here. Because the relationship there is 531 kcal over 3 moles of CO2. In this case, there's 1, 2, 3, 4 relationships to the 531. This just happens to be 1 mole, so the other one had a 1 here. But if asked how much CO2 was produced, then I'll have a 3 here over the 531. Times a 3. So what you meant? The first one.
No. Yeah, I'll talk about the first problem that you did. Of this.
Like 3 minutes ago, a different problem from this.
Just seeing how much the propane.
Okay.
You just got, the.
How much propane was burned?
Yes.
Oh, I should have changed that. Okay, that's how you would solve this one, just the way it's written.
So I would just, my answer would just be 0.00, but I have to add times 10 to the
1.24
3.
divided by 5, 531. 3 significant figures, so 3, 4 times 10 to the 5.
So I wouldn't, so I have that like 2.34.
That's 100% correct, but if that's not in the answers,
Okay.
then what might be in the answers is this. 10 to the 1. I gotta think here. 10 to the 5, 432 times 10 to the 2.
Okay.
Okay. So this one you came up with the moles. This one's asking for grams. If you're given moles, given some amount of energy, find the moles. Another one is given some amount of energy, find the grams. So the same reaction. 6.70 times 2 to the 4. that's how much energy is released. And now it's asking you how many grams of oxygen were consumed. This is number 6. 6.70 times 10 to the 4 kcal. We're talking about O2 here, 502, so we have is it 530? So there's that relationship. 5 moles of O2, 531 kcal. And now we need the grams per mole. Which is 2 times 16, so this is the grams per mole for oxygen. And that'll tell you how many grams of oxygen were consumed when this much energy came out. Does that make sense? So this is really a review. I don't think I did any. I only did the ones where you tell how much energy. I didn't do any that told you how many more. So that's the basics of delta H. We did estimate delta H from bond energies. So the rest of this stuff is about how would you estimate it. If you didn't actually do the reaction yourself, how could you estimate the energy? And one of the ways we did it was with bond enthalpies, that is bond energies, last time. So the new way to do it is this is section called Hess's Law. Section 9.8, the exercises here are 75, 76, 77, and 78. And I will make quizzes for the bond energy estimates, and I'll make a quiz for the bond energy and a quiz for doing this. But this is how it works. So if you're told so here's what you're given for these types of problems. You're given the reaction, and it's saying, okay, what is the delta H of this reaction? One way to do it would be to break up and figure out what are the bonds being broken here, and what are the bonds being formed, and then you use that chart that has all the bond energies in it, the way we did it last Friday. Here's another way to estimate bond energy. You can typically find what we call standard delta H. That's what this little O is here, there. You can generally find these tabulated in various places, and if you've got the right set of reactions in front of you, you can estimate this by playing this little game I'm about to show you. So this is Hess's Law. I'm about to show you. So this is what you'd be given. Here's a reaction, and it's saying, what is the delta H of this reaction? And you're also given this little set of other reactions. So what you want to do first is go, okay, I need N2 on the left side of the arrow. And you look down here and you find the one that's got N2 on the left side. You look for one that has N2 on the left side. There it is, N2 on the left side. So the first thing I'm going to do is write down this whole reaction. 1/2 N2 plus 3/2. These are the coefficients, these fractions. Since I didn't have you guys do a lot of balancing, we didn't go too much into it. You probably haven't seen these fractioning things, but you can have a fraction for the coefficient. Instead of a whole number, like a 2 in front of this, you can have fractions, so don't get confused there. Plus 1/2 H2 HN3. Delta H for that reaction given is negative 174 kilojoules. Now, I also am going to need O2 on the left side. And you look down here and you go, okay, that has O2 on the left side, so I'm good there. I've already got O2 on the left side. I'm also going to need into O2 on the right side. And I look over here on the right side, and I don't have into O2 on the right side for any of these. But I have into O2 on the left side here, so here's what I'm going to do. I'm going to take this and flip it backwards like this. I'm going to put 2 HNO3 makes into O2 plus H2O. Guess that's okay. When you take this and flip it over, you change the sign. So now I'm going to put positive 76.6 for this. So that's kind of one of the rules to follow. If you have to flip around one of these, flip it around backwards, you change the sign. Why do I think that's not balanced? 2 times 3 is 6, 5 is 6. 2 of those, no, it's balanced. Okay. Good, all right. So now, I have everything I need. What you can do when you have a reaction like this, it's kind of like just adding things up. I have, on the left side here, I have 1/2 N2 plus 3 halves O2 plus 1/2 H2 plus 2 HNO3 makes HNO3 plus N2O2 plus H2O. And since I'm trying to make this reaction, the problem I have here is I've got H2 here and an HNO3 here when I just wanted N2 and O2 on the left side. So I've added up everything here and added up everything here, and what that tells me is I need another reaction to get this stuff.
Can you just add in reactions?
Yeah, I literally just added them together. I added everything on the left side down here, and then I piled up everything on the right side down here. You follow that process? So this doesn't get me to the reaction I want, but it gets me close. What I need now is, which one have I not used? I used that one, I used that one, okay, this one. So to get rid of 2 HNO3, I need to get rid of the HNO3. Here's the other thing I can do. One of the things you can do to eliminate, I thought I could solve this on the fly and now I'm stuck. I need to get rid of, okay, the HNO3 doesn't show up anywhere up here, so I need to get rid of it. The way I can get rid of it is look first. Grab that one off the web. Stick with one a little complicated one is not, okay. Okay, let me do 76 in the exercises. Let me do this one instead. It'll go a little smoother. The more of these you have to work with, the harder these are. And here I am trying to do it on the fly in front of you guys, and I'm getting stuck. So let me do one that only has 2 of those. Not 75. I'll do 76 because 75 gives you the answer very accurately. Okay, this is. All right, here's what you're given for number 76. CAO. That's the reaction. And the question is, what is the delta H of this reaction? You're also given it tells you this delta H. Given one other one, 2Ca plus O2 equals delta H. That one is so that's what you would be given for a problem like this. Okay. I need CaO on the left. None of these have CaO on the left. There's CaO on the right. So what I'm going to do is I'm going to take this one, but I'm going to flip it so I have 2CaO, 2Ca plus O2. And the delta H I'm going to list for this now is this, but I'm going to flip the sign. 1269, 8 kilojoules. So now I have a reaction that has CaO on the left. I also need CO2 on the left. And I need CaCO3 on the right. So this one has CO2 on the left, like I want, and it has CaCO3 on the right, like I want. So I'm going to write that one as is over here. Ca plus CO2 plus 1/2 O2 makes CaCO3. And I'm just going to copy it over negative 812 kilojoules. All right. Okay, what I want is on the left side CaO and CO2. CaO and CO2, but I need to get rid of these two somehow. You with me? Because if I just add these up, if I drew a line and I just brought down what was there, I would be bringing down some CaO and I would be bringing down some CO2. That's what I want. But it'd also be bringing down some Ca and I'd also be bringing down some O2, which I don't want. But the way you can get rid of things is if it's the same on both sides, meaning I've got 2 Ca there and 1 Ca here, if I can get 2 Ca here and 2 Ca here, I can eliminate them. So watch what I do here. I'm going to multiply through all of this times 2. 2 times everything there, including the delta H. So watch what it does to this. If I multiply that by 2, I'll have 2 Ca. If I multiply that by 2, I'll have 2 CO2. Multiply by that by 2, I'm going to have 1 O2. If I multiply that by 2, there's a 2 there. And then negative 812 times 2 Now this is times 2, which is negative 1624. So there, now I multiply everything by 2. 2Ca there, so I can cancel them. And I've got O2 and O2 there, so I can cancel those two. And now when I bring everything down, I have 2 CaO plus 2 CO2 plus 2 CaCO3. Maybe the better thing to do would have been to multiply this by 1/2. So that's what I brought down. But let me do a better strategy here. Ca plus CO2, 1/2 O2, CaCO3. So I just undid the multiply by 2 because that didn't turn out to be the better strategy. The better strategy is to multiply through this by 1/2. 1/2 times all of this. And that's still going to do the same thing. It's going to eliminate the stuff I want to eliminate, but I won't have those coefficients. So 1/2 of 2 is 1/2 times 2, 1, so I'll just erase that. 1/2 times 2, 1, and 1/2 times 1 is 1/2. And then I still have to multiply 1/2 here. So 12.69, 1269.8 divided by 2, 634.9. That will give me this. If I bring things down now and eliminate, I can eliminate what's on both sides. I can eliminate that and that. I can eliminate that and that. And now what I bring down is CO2 plus CaO. The way I did it before, I had a 2, 2, and 2, and I could have just multiplied by 1/2 from there. But the whole point is, I've added these, and now I'm going to add these. 634.9 minus 812. Actually, I can put reaction here now. Reaction. You see the process I'm trying to go through here? I know I'm doing this kind of messy. I'm not doing a great job explaining this. Let's do 78. Oh, this one has 3. Well, I'll give it a shot. Either I can do it or I can't. 278. 78 gives us 3. So here's the reaction you're trying to create. CCl4 plus 4 HCl. That's what I'm trying to create. The reactions I'm given to work with are that one. This one will be easier than the one I try to do first. gives you these balanced equations, and it gives you their delta H's. Which is negative 95.7 kilojoules, negative 92.3 kilojoules. Okay, so this is what we have to work with. And we're trying to create this. Let's see if I can talk through the process without making it seem so messy. So I'm just going to start up here with this. I need CH4 on the left. All my equations here, this does not have CH4 on the left, this does not, this does now. That's not CH4, that's not CH4. Here I have CH4 on the right. So what am I going to do? Flip it. So I'm going to write this the other way around. CH4 makes C plus 2H2. And I'm going to change the sign. Delta H equals 74.7. All right, so far so good. All right, now I need 4 CLs on the left. I can get 4 CLs. Okay. I've got CL here and CL here, so let me save that one. I need CCl4 on the right. This one has CCl4 on the right, so I'm just going to rewrite this one the way it is. C plus Cl2 yields CCl4. And that delta H equals negative 95.7 kilojoules. I also need, so I skipped this one because I had 2 of them that had CL. But if I go on, it's all going to work out because you're always going to be given equations that do this, that do what you want it to. CCl4, okay. I've got CCl, I've got this on the left, I've got this on the right. I need this on the right. This one has HCl on the right, so I'm going to grab that one. H2 plus Cl2 makes 2HCl, and it's delta H equals 92. Okay, so I've used all 3 of them. So we're going to end up being good here. This is just going to fall into place once we do this. I need to eliminate, so this is just carbon by itself, and carbon by itself doesn't show up anywhere, so I need that to go away somehow. Meaning, I'm going to need to be carbon on the right and the carbon on the left. I need them to equal each other so I can eliminate them. As it stands, I can't eliminate them because there's only one of each. What is it I want to do? I've got 1 CH4, that's good. I need 4 CLs here. Okay, cool. All right. I need 4 CL2s. I've got 1 CL2 there and 1 CL2 there, so I've got a total of 2 CL2s, but I need 4. I think what we need to do is multiply by 2 and multiply by 2. Yeah. If I multiply by 2 here, I'll have 2H2, and I'll have that 2H2. So I'm going to multiply through all of this by 2. So 2H2, 2Cl2, this will be a 4HCl, and then 2 times 92.3. 2 times 92.3. So now it's negative 184. 6. So what I did is multiply everything by 2, including this. Now I've got 4 HCl, that's good. I've got 2 Cl there, I don't have enough Cl. I have 2 H2, so those will eliminate. So now the next thing to do is multiply through here by 2. And I've got 2 CCl4. something's still wrong. Did I copy those correctly? See, 2H2. Oh, there was a 2 here. CL4, 2HCl. So there was a 2 there. Sorry, that was a typo. This one I just took as is. I think that does it then, doesn't it? I can eliminate that. I can eliminate that. Then I have 4 CLs. So, yeah, that works. Okay, sorry. There was supposed to be a 2 there. But I took this one as is and wrote it over here. So all I've done so far is flip this one. I flipped this one backwards. So this became positive 74.6. And the other thing I did is I multiplied this one through by 2. So that gave us 2H2, 2Cl2, 4HCl. And then I multiplied that by 2, which gave us 184.6. You with me? And this does it. If I sort of add this up, I'm going to add these to get this delta H for this. But if it's the same on both sides, I can eliminate it. So eliminate the C, the 1C. I can eliminate also the 2H2. And that's it. Over here I have CCl4, HCl. Neither of those show up over here. Over here I have 2Cl2, 2Cl2, and CH4, and none of those show up over there. So what I have left is CH4, this, plus this, which is 4Cl2, so I add those up. And then I've got CCl4 and 4HCl. And that's this. CCl4, you see that? This does take a little thinking. You see me stumbling around, but you have to just kind of work on it until you get to where you want to get it. Typically, you're given everything you need here. Sometimes I've seen these with red herrings in them, but I don't do that. With something you don't end up needing. But you're always given what you need here. And then the last thing to do is to add those up. 74.6 minus 95.7 minus 184.6. So 74.6 minus 95.7 minus 184.6. So what I get here is delta H equals negative 205.7 kilojoules. So Hess's law just says that if you have reactions that you can manipulate this way to sort of add up to this reaction, you can also use the delta H's here. And it's a way to estimate the delta H of a reaction that you don't have a standard. Like somebody went and measured this reaction and they found that it was negative 74.6. Somebody measured this reaction, they found that it was negative 95.7. Somebody ran this reaction and found that it was negative 92.3. And then here you are with a reaction you want to do, but you can't get into the lab because it was flooded or something. And you're like, well, gee, what would the delta H be for this? You can take these reactions that somebody's already done, manipulate them with some algebra, and estimate what the delta H is for you for that. Does that make sense? I know I went a little messy with it, but the only thing to do with these is to start trying to work with them. So I would say you guys try to do this one and this one on your own. And I will get some quizzes up with more of these so you can practice with this more. Okay, Hess's law. What else? Did Hess's law. Okay. The more fundamental thing is heat capacity, and I did start this a few weeks ago, and then I said, I'm just not gonna put it on test 2, I'll do it on test 3, so let me go back to this. Heat capacity and specific heat. And that's section. Exercises. And I'll get some quiz up on that too. This is the one, if you go back to PowerPoint. This list of heat capacities, I'll give you some tests. You're going to have to be given heat capacities to solve questions like this. You're given answers to 43, so I won't do that. 42, 42. How much heat is required? Kilograms. Sand. These are always degree C. At least for any of the questions I'll give you. Okay, what I need here. Table 9.2, I'm going to get this from table 9.2, which is, I'll give you that table on that test. I'll give you any specific heats you need. This says for sand, and the units are joules per gram per degree C. Those are the units. Another way to say that is for every 1 gram of sand, you can change it 1 degree C if you put 0.84 joules of energy into it. That's the heat capacity of sand. So we need that to solve this. You're given 2.50 kilograms. Since this is in grams, I'm going to need to translate that into grams. So I'm going to go 1 kilogram is 1,000 grams. I'll be more formal here. 2.50 kilograms of sand. 100 grams of sand is 1 kilograms of sand. All right, now I'm going to use the heat capacity. Grams is on top. We'll have grams on top here, so I want grams on bottom, so I'll use it this way. I'm not going to flip it over. So 0.84 joules. 1 gram to 1 C. maybe I should do the delta. No, that's fine. I'll just do it. Okay, we need delta T, the change in temperature. Delta T is temperature final minus temperature initial. So here, our delta T equals, our final temperature is 100. And our initial temperature is 25. That means our delta T is 100 minus 25. The delta T is plus 75 degrees C. And that'll end in joules. I was thinking maybe I should just put the 75 first. It really doesn't matter, but that's how you calculate it. So kilograms cancels, grams cancels, the degree C cancels, that'll give us joules. That'll tell us the heat. Heat is a form of energy, so. You follow that? All right. Remember what was that?
Will you go through the final answer?
Oh, you want me to calculate? I get 2.50 times 1,000 times 0.84 times 75, and it's all 1 on the bottom, so I get 157,500. We end in joules. You could put, because it's, what do we have? That's exact, that's exact, that's exact. Exact, exact. 2 significant figures there, 2 significant figures there, 3 significant figures there. So we need to end in 2 significant figures. The 7 rounds to 5. So 160,000 joules. Or you could put 160 kilojoules. So that's the correct answer. Because there's no decimal here, this says 2 significant figures. You could also do it as, that's 100% correct as well. That's just in joules and that's in kilojoules. And you could also go 1.6 times 10 to the 2 kilojoules. That would be 100% correct. You could also go, what am I thinking here? So these 2 and those 2 are all 100% correct. If you're not asked to put it in kilojoules, you can leave it in joules. If you're not asked to put it in scientific notation, you can do that. You guys okay with that? All right. So here we were given a change in temperature and some kind of, well, not grams, kilograms, grams. And then we found joules. So that was number 42. That was number 42. Okay, 44. Here we're being asked for a temperature. Unknown mass of substance. So let's look at 44. says no mass of absorbs 1.95 times 10 to the 30 joules heat slash energy. Final temperature is that's essentially what you're being asked for 44A. You with me? To solve it, I look up on table 9.4, table 9.2, for Pyrex glass, it's in there. Joules per gram per degree C. That's what I've got. 1 gram, 1 degree C is what I get from table 1.2. So I'm going to need that. We're looking for a final temperature. No, we're looking for mass. All right, so let's go ahead and get our delta T. Delta T equals, final temperature is 55.4. Initial temperature is 23.0. .4 minus 23.0. So our delta T is 32.4 degrees C. So we have that. We have our joules. End on grams. All right, since we need to end on grams, I know that I'm going to use this flipped over. That's what we're being asked for, how many grams. So I know I'm going to need this flipped over, so I'll just key on that first. 1 gram, 1 degree C over 0.75 joules. That puts joules on the bottom, so I'm going to take this, put it on top. That's the joules. What else do we have? We have delta T. Since we have degree C on top, we want the delta T on bottom, 32.4. So now I use this. That does it. Joules cancel. No. I want that on the bottom, 32.4. So joules cancel, degree C cancels, and we're left in grams, and that's what we want. Does that make sense the way I did that? It's 1 times 1 times 1.95. I'm going to leave the 10 to the 3. divided by 0.75, divided by 32.4. Calculator says 0.0802469, blah, blah, blah. And I've got to put the times 10 to the negative 3 there. I just wasn't 10 times 10 to the negative 3. And it's joules. No, it's grams. Grams. Maybe grams. All right. What else do we need to do? Two significant figures, 3, so we need these two. So 0.080 times 10 to the 3 grams. That is 100% correct. If I did the 10 to the 3, though, I would go 1, 2, 3. So that's correct. But if I did the times 10 to the 3, 1, 2, 3, I would have 80 grams. That's also correct, but I need to put a decimal there to indicate the two significant figures. Scientific notation, you can do 8.0 times 10 to the 1 grams. You wanted standard scientific notation. You guys okay with that? All right. Maybe I should do. Yeah, let's do one from 43, because it's actually slightly different. Let's do 43. This time it's asking for an initial temperature. It's asking for a final temperature. Let's do 43. All right. This time we're working with gold. And what you're being asked here is 25 grams of gold initially what is the final temperature of gold upon absorbing 2.35 kilojoules of heat, aka energy. Okay, we got grams. Okay, we're going to need a final temperature. We need gold. So gold from the table. Look up the table, you find gold. It says 2.35. Joules per gram per degree C, or 2.35 joules to 1 gram to 1 degree C. So we need to end on a temperature, so we need this on top. 1 gram times 1 degree C over. So I'm starting with this flipped over because I need to end on a degree C. I've got joules on the bottom, so I'm going to take these joules and put them on the top. So that takes care of the joules. The grams is 25. I put it on the bottom because these grams are on top. So now grams cancels and joules cancels. Oh. They gave us this in kilojoules. So we have to go 1 kilojoule is 1. Since that's in joules and that was kilojoules. So now joules cancel, kilojoules cancel, and grams cancel. That leaves us in degrees C. So what that's going to give us is the delta T. And then we'll calculate the final temperature using that. So let's find delta T. All right, 1 times 1 times 2.35 times 1,000 divided by Did it say 2.35? Did I get that off the gold is 0.128. If you look on the chart, that's actually what it says. That's what it says for, we're doing gold, right? Yeah, okay. If you look at table 9.2, this is actually what it says. So I needed .128 there. This came from the problem. All right. 1 times 1 times 2.35 times 1,000 divided by 0.128 divided by 25. Can't be right. Joules cancels, kilojoules cancels, grams cancels. I just have this huge number. There's no way that's right. This is where I got hung up last time I tried to show you all this. 2.35 kilojoules of heat, 25 grams, 27. I just get this huge number here. 2.35 times 1,000 divided by 0.128 divided by 25. I get this, now I get 734. Anybody else calculate this? 2.35 times 1,000 divided by 0.128 divided by 25. Okay. That's what I got, 734.375 degrees C. We can only get, now I guess we can only get 2 significant figures here. That has 3. So 730 degrees C is the delta T. Delta T is temperature final minus temperature initial. We'll look this one up. Initially at 27 degrees C, delta T is 730 degrees C, and then 730 plus 27, 27.0 equals temperature final, which is 730. If we follow the rules, I get the feeling they didn't. addition subtraction rule says this has 1 after the decimal, this has nothing after the decimal, so our answer has to have nothing after the decimal. So when I do this, I get it started at 27 degrees. You put this many kilojoules into it, and it goes all the way up to 757. Let's just see if I screwball that or not. 43A in chapter 9. Yeah, I guess we did it right. Get 757. Two significant figures. Oh yeah, that's right. If you did this correctly, it's still two significant figures. The way I taught y'all before, I would underline those just to emphasize it's only two significant figures. So this rounded to two significant figures is 760 degrees C, or 7.6 times 10 to the 2 degrees C, which is what they have for the answer. They have the standard scientific notation for the answer. Oh, we did that correctly. For something like that, I don't guess I would, my A, B, C, D, and E answers wouldn't play a lot of games with the significant figure stuff there. I guess they did that correctly. You guys follow that? So we found delta T for that one. And then we used the delta T as initial temperature to find the final temperature. You guys okay? All right, I think we can just kick it right there. I'll do the heats of formation next time. Let me get back to this later. So we did this. All right, we're down to just heats of formation, and then we'll go to chapter 10. Oh, we still have to do calorimetry. That's not on the list. We'll probably do next time. We'll do next time we will do. Calorimetry is chapter 9. I guess this is for Ellie, in case she wants to be ready. But 9.7. This is just discussing how you actually measure the entropy. And we'll be doing a lab that way. Okay.